Thank you very much. Like I said, I'm Noah. I'm an SRE at Geomagical Labs. We do computer vision and augmented reality stuff for IKEA. That's not what this talk is on. I'm also not really here to talk about Python, like Chris said. Python is great. It is my primary tool for problem solving. But there's a lot of other programming languages out there, and some of them have workflows or tools or features that Python lacks. My goal of this talk is not to immediately advocate we turn every one of these features into a PEP. Instead, I want to broaden our exposure to programming concepts and talk about the trade-offs being made. But hey, if one of these ideas really grabs you, maybe try messing it around in a library or see how it would work as a patch in CPython. I'm going to begin with PHP. I don't mean this to be ironic or to be a language hipster. PHP is actually pretty cool. I spent the last few years on a side project that's almost entirely in PHP, and it's given me a refreshed appreciation. Biggest thing I've grown to like about it is the simplicity. Each file maps unambiguously to a single URL, and deployment is as simple as updating that file any way you prefer. Most editors these days also support remote editing over SFTP, so you can just click New File and start typing. This puts even low boilerplate web frameworks in Python to shame. And once you get going, the changes in the code, they'll be there automatically. There's no need to figure out automatic reloads or hot reload configs or whatever it is. You just write code and it runs. In Python, we like to say that explicit is better than implicit, and overall I agree, but man is juggling imports annoying sometimes. Even with editor help, the dance of write a line of code, scroll to the top of the file, add the right import, scroll back down, it's just annoying. Autoloaders bridge this gap while keeping things mostly explicit. If you enforce a one-to-one mapping between the code symbol and the file system path, you know exactly where that symbol load is going to end up. This is also deeply integrated into the package manager, Composer, to pre-bake the mapping between class names and files so that it doesn't even have to scan a package directory. Honestly, I'm not entirely certain I would like this in a system like Python, but it's good to at least know about. The standard library for PHP is a little different from Python. It's evolved to its specific niche, web application development, so it biases towards things needed in that space. MySQL and Postgres clients are included by default, so is a high-performance HTTP client. Outside of that, PHP has this thing called the PHP Extension Community Library, or PECL. So an extension in PHP is specifically something written in C code, so it's a little bit more heavyweight than a normal composer library. But the main difference between PECL and PyPI, the docs for the mainline PECL things, the PECL extensions supported directly by the PHP team, live in the standard PHP docs. So for those things, you don't need to go to GitHub and find a package and find its docs. Maybe they're on read the docs, maybe they're on README. It's all just in one place. Alongside the standard library being adapted to its major use case, the language is too. It's web first, so simple templating is directly baked into the language. We have F strings now, so we're kind of evolving a little bit in this direction, but again, really basic PHP will run circles around really simple Python is way more complicated than even really complicated PHP. Ruby is probably my second most used language. Chris mentioned I used to help run a Ruby project for a lot of years. The days of Ruby and Python kind of being thought of as a unit in our collective imagination are kind of waning, but it's still a vibrant language and a vibrant community. Symbols are a thing in a lot of languages, but I'm going to highlight them here. At their simplest, symbols are just fancy strings, but they're internally deduplicated, so comparing two symbols is a constant time operation. We do have this in Python with sys.intern strings, but they're really rarely used. It's a little bit awkward, and there's not a whole lot of reason to want to reach for it. But this is a bit misleading because there's a deeper reason for symbols to exist. They differentiate between text strings and, for lack of a better term, symbolic strings. These are pretty often the same data type, but they serve vastly different functions, and they shouldn't be mixed. We already kind of have this in Python with the keyword argument syntax. We know that's a string of a sort, but it is obviously kept separate from the textual data that you're working with. String enums are also kind of like this. They are a string under the hood, but they're obviously a different thing, although that's kind of different from symbols. Blocks are something more specific to Ruby. Again, deep down, this is something Python has too. We have Lambda expressions as anonymous functions, but blocks do a bit more than that. First off, they aren't limited to being a single expression, which is handy if you're doing anything a little bit complicated. And second, the calling syntax with do lets you easily hang a block off of any function in Ruby. Now, you can pass around Lambda literals in Python, and it's even readable sometimes, like say for sort keys. But the utility falls off pretty quickly. So community practice is to instead declare an inline function and then pass it as a normal argument. The problem with that is it results in backwards code, where the read order of the code is the reverse of the execution order. And this gets much worse when we get to method chaining. I'm not even really going to talk about the Python standard library functions because they are the absolute opposite of this, and I hate it. But we can build method chaining in Python. The Django ORM and query set API is a great example of this. But blocks let you go a lot further in less effort. And another language that has a different take on this is Dart. It has this double dot cascade operator. It allows you to go one level up in a chain, so to speak, kind of like in a file system path, and perform a sequence of operations on the same object. Normally with method chaining, this works by every object in the chain is effectively returning self. Dart's cascading operator, you don't even have to do that. So you get all the benefits of method chaining with no work needing to be done by API authors. Another place where Ruby makes excellent use of blocks is the builder pattern. Many complex object constructors take a block which exposes a little configuration API, and this can allow really compact initialization without sacrificing flexibility for special cases, and it's a lot easier to deal with static typing than in Python, where we'd usually be passing in like a giant nested dict. Going a bit broader than Ruby, as a language, is Ruby as a community. One thing that Ruby has that I really wish Python did is the Ruby for Good organization. It's a dedicated support structure for Ruby projects that work with specific nonprofits to try to advance some aim that isn't Ruby itself. They are there to do good for the world. We certainly have a lot of paths for advancing Python. PSF is great, and you should support it, but the PSF exists to support Python, not to go and do great things with Python in the world. That real tangible good is a thing that I wish we had a better way to deal with. So after Ruby, the next logical place to look is the JavaScript and TypeScript worlds. I'm not going to repeat every feature that every one of these languages has, like JavaScript also has a really nice anonymous function syntax. We'd be here all day, so let's just focus on the interesting bits. This one has already been discussed at great length in the Python community, but I personally think they should be added, and it's my talk, so one more time. Null coalescing operators are very similar to OR, but instead of looking for a falsy value, they're looking explicitly for none. Safe navigation operators build on this idea that you can have a deeply nested chain. If anything during that returns a null, it'll just bail out and stop executing the chain. As you can see from this really simple example at the bottom, it dramatically streamlines even simple code. I deeply miss these when I'm working in Python now. TypeScript has always had a really fine line to walk. It applies type semantics to JavaScript, but it can't fundamentally reshape the language or it would be too alienating. So the designers of TypeScript knew that basically every object passed around is going to be what in Python we would call a dict. They also wanted to allow typing to be added gradually to large projects, because doing it all at once, it's just never going to happen. Out of this comes the synthesized requirement to support inline type declarations against arbitrary dicts. In Python terms, this is kind of like typed dict, but you can't do typed dict inline this. We also have data classes now, which is cool, but that would require upstream and downstream to potentially have to change. We don't want that. This isn't as nice as a fully typed code base. I am never going to say that, but this is a great on-ramp for doing one small bit of code at a time. I'm kind of cheating here. We do actually have promises in Python. They're in the concurrent.futures library. And also, possibly their moment is just over with the continued growth in explicit async await APIs, both in Python and everywhere else. But they're still worth studying, even if only as part of our collective history. Promise chaining is a compact way to express multiple interacting concurrent operations without dedicated syntax. I'm pulling my punches a bit because this is a really simplistic example. In practice, many promise chains were substantially harder to read, but maybe this technique will find another use someday. On the topic of concurrency, Go. It's no secret that Go's structured concurrency has made it a frequent choice in complex systems code. And honestly, I think Python is already heading in a lot of the same directions. So if you've seen anything about Go, it's probably this. Go routines are a lightweight concurrency mechanism, kind of like we have with async functions, except they are truly concurrent, and they have channels, which are these little queues to move small bits of data between them. I think this model is about to get really interesting in Python because of the work that's being done over 3.12 and 3.13 with GIL-isolated sub-interpreters. There's hopefully a near-term future where we get something really similar to Go routines, but in Python and achieving true multi-core concurrency. Runtime type checks are something Python's always kind of kept at arm's length. We do have some really basic ones. There's this decorator called runtime checkable on the protocol in typing that you can use with protocols. But all it does is check that the named methods exist. There's nothing in Python that will actually compare a type signature, so we can't do that. Compare this to Go's runtime casts, which do an actual complete interface check, and they can either return an error or crash, depending on what you'd prefer in the code. This is something that would require that CPython implement a way to compare type signatures, but maybe we've come far enough to be ready for that. In a totally different direction, Go is among the best in class, alongside Rust, for easily building standalone executables, as well as cross-platform compilation. In the server world, this makes deployment inside containers really easy, because all you need from the OS is a couple of TLS certificates, maybe a time zone definition or two. And for command line tools, you can distribute a single binary without having to worry about system library versions, or they've corrupted their system Python, or whatever else. Briefcase has recently added relatively simple CLI packaging support, and I'm really hopeful it's going to improve things here. If you're only here for things with an even tiny chance of happening in Python, I wish you well, but now I want to look at the long tail. So these are weirder features. You've probably heard about some of these, but it really seems unlikely Python is ever going to even seriously discuss these, but I think there's still stuff here to learn. On the complete opposite end from easy packaging, easy one-liners. Perl has lots of interesting design elements, but the one that is by far most useful to me on a day-to-day basis is PerlPy. This is a sequence of command line arguments that say, take a list of input files, run an expression on each line of each file, and then write the output back to those files. Taken together, this allows for a superset of sed, awk, and bash loops without having to worry about the provider variances of all of those tools. Now, there is definitely the ability to do this in a library, and in fact, there are some on PyPI already, but part of the real value of PerlPy is you can parachute me onto any server made after about 1995, and there's probably a Perl binary somewhere on that system. Maybe if we add this to the standard library now, in 10 years it can be similarly omnipresent. LINQ is short for Language Integrated Query, and it's basically, what if SQL was our API? Now, the most direct use of this is using it as an ORM, and C# does plenty of that, but C# took it even further. You can add an arbitrary provider in C# code that exposes a LINQ API. Python's already taken some baby steps down this path. We have some of the new cross-library standards for data frames, and we have DuckDB on top of that that lets you write effectively SQL queries for your data frames. But what if that was language syntax that not just DuckDB, but anything else could plug into? Call with current continuation is going to take some explaining, so just bear with me. At a basic level, it's a kind of non-local return, like an exception. And indeed, you can see an example here of implementing a really basic version of callcc using exceptions. The idea is you run a function, it takes a callable. When the function is ready to return, it calls that callable with the result. And then it jumps back into wherever the continuation was generated from. This alone would be pretty boring. The real value of continuations is that they can be moved around, stored, and in some languages even serialized, just like any other value. This makes it kind of like a structured go-to. Imagine if you could save and restore the state of a generator function like any other value. While continuations are most associated with Scheme, they're used really effectively in the Smalltalk web framework Seaside. So in Seaside, the whole state of the application is managed via pickleable continuations. So that invocation of color picker you can see in that code there, this is a server-side application. When you call color picker like that, it's going to send a response to the browser to please open a modal to display a color picker to the user, wait for the user to pick a color, send a request back to the server, and then pick up right where it left off. This is all the cleanliness that you get in a client-side single-page application, but in server-side code. And because I really love how Smalltalk does flow control, here's a really rough port of a tiny bit of it to Python. The short version is Python doesn't have special syntax for flow control. It's all implemented via pure object-oriented methods. So if is a method on Booleans, so is while. The practical implementation of these, they do actually generally get optimized in special constructs because reality exists, but it's still a great example of doing more with less in language design. And if you want to get really, really minimal, you can dive into tiny fourths. You can bootstrap an entire language interpreter with a few hundred bytes of assembly, 20 to 30 keywords. From that, you build a parser. From that, you build an interpreter loop, control flow, and whole programs. Fourth kernels have been written as small as 400 bytes of machine code. Minimalism is not a specific goal for Python, but it's a good reminder of what little you need for a productive system. What would a minimal Python look like? What is the smallest amount that we could write to then write the rest of Python in that? Another interesting blend of language features and frameworks is Erlang's Open Telephony Platform, or OTP, specifically the supervisor system. Erlang programs are, to use Python terms, a series of async tasks all running in parallel. We can certainly do this in Python, and we kind of have this already with task groups a little bit, but it's a little bit difficult to figure out when something does crash, what do we do about it? OTP applies similar concepts as server management or container management, but to individual tasks within an application. We can configure a restart behavior, customize how the restart is going to work, build dependency trees so that when one thing restarts, it automatically restarts an entire dependency chain. This is how Erlang builds incredibly high uptime systems like phone switches without magic programmers who never write bugs. This could mesh really well with the subinterpreter work we were talking about before when we were talking about Go. And in fact, Go's coroutines and channels were heavily influenced by OTP's server and mailbox system. So we could have a future where task groups are not just a synchronization mechanism, but also provide some kind of runtime supervision themselves. I started off saying the idea of this talk wasn't to go and turn all of these into PEPs. And while that is true, I wish it wasn't. A few of these ideas could probably be prototypes in libraries, and they could gain traction there, but most of these would require some kind of core language change. The process for that has improved over the years, but the steering council has a really fine line to walk because adding something to CPython is a big commitment. This leaves us in kind of a bind. To get peer support for a new change, we need to have that change in core, but to get that change in core, we need existing peer support. Macros are a language construct that allow metaprogramming inside the language itself. Add new syntax, change something that's already there, write your code in Rot13, the sky's the limit. The two best places to look for ideas about macros are Rust and Lisp. C does heavily feature macros, but it takes a much less structured approach. It's just treating your code as text to be templated. Lisp and Rust show a deeper power, defining macros in terms of the symbols of the language, but not its syntax so we can create our own. Python does have a proposed macro system, heavily influenced by Rust, allowing user code to register a macro provider at compile time, which takes an abstract syntax tree and is allowed to arbitrarily transform it. Unfortunately, this proposal itself seems to have fallen into the same trap we were trying to escape and has had little discussion over the years. I want to talk about how Lisp does macros, but before we can do that, we need to talk about how Lisp code is structured, and before we can do that, we need to talk about how Python does that. Like most other languages, Python's parser produces an abstract syntax tree, or AST. This is not yet the bytecode that's going to actually run, but it is a highly structured form that is ready for compilation into bytecode or something like that. Lisp does do this, but it's far, far simpler. Every piece of code turns into one of two things, either an atom or a pair of other things. Compared to Python, this is just the barest bit of structure, but it also means that macros can do almost anything you want as long as both the input and output are S expressions. So the way def macro works, very, very roughly speaking, it fully parses your Lisp code into S expressions, and then it starts looking for special atoms. And def macro is a special atom that it knows about. It takes an atom for the name, atoms for the arguments, and then a code expression to evaluate when invoking the macro. If it later on sees that name in your code, it will also recognize that as a special atom. It'll take the arguments, which remember are purely symbolic at this point. They have not yet been compiled or run. It doesn't know anything about them other than that they are an S expression of code. It runs the macro code on that expression and puts the resulting thing back in the original code. The important takeaway here is that macros break the usual flow of things. Usually our code moves linearly from tokenizing to parsing to compiling to executing. Macros put their own little subloop inside the parser step, where you're compiling and executing the body of the macro, returning its output to the parser, doing that over and over until macros have all been expanded. This might seem like a minor thing, but it's the pressure relief valve that lets us extend the parser in a standalone way without the person maintaining that parser having to do any extra work. Rust has two types of macros, really. Procedural macros are basically the same thing we just saw with Lisp. They're a little bit fancier depending on which kind of part of the parser you want to hook into, but at heart, they're all functions that take a stream of tokens and return a stream of tokens. This allows effectively unlimited control because this is operating directly on tokens rather than expressions. It can even do things that aren't valid Rust syntax in the first place. But usually when we're writing a macro, we don't want to go quite that far, so there's a second, simpler system called declarative macros, or just macro rules. They're similar to a Python match case statement, but the parameters are symbolic expressions or types, and the code block is returned rather than executed. The system goes way deeper. You can still do some basic templating, but I can't really do that in 30 seconds, so hopefully this gets the idea across. Almost any idea that you can imagine in Rust can be prototyped inside a macro. Why look at all of this? Personally, I just think it's fun to see what's out there. But if that's not enough, I certainly hope that learning all these systems and patterns can help you better organize your code and APIs and shows you what other tools are available if you need to use them, and in the end, that makes us all better developers. Thank you very much.